A very good morning to one and all. And today I'm explaining another example for the construction of the PDA. And let's see what the example is. And here from the given language, we're constructing the PDA, right? So what the given language is, and the language is WW power R. What it means is string reversal. For example, if you're taking a string like in 0 1, that means already I'm having an alphabet, the input alphabet zeros and ones here. So from this I'm taking the string 0 1, and what the reversal of the string is 1 0, right? So for such type of a language, first what you need to do is you need to design the context free grammar. And by accepting the language, this is the context free grammar we designed: 0 s1, 1 s0, or epsilon, right? So this is the context free grammar for the given language. And now what we need to construct here is we need to construct, or we need to design the PDA for this language. And here, for constructing the PDF, first you need, I think you all know how to design the CFGs, how to construct the CFGs, right? And from that you are designing the PDS. From by knowing the construction of the CFG, you are designing the PDS. And it is very easy for you all to know how to design the CFGs. And initially we just make a symbol with the S, that is S is a starting symbol. With the starting symbol S, we design an CFG for the string reversal. So these whatever the rules that we're having for this, those rules, all the productions are acceptable for the language. And now coming to the PDA, and here the PDA is defined with an 7 tuples, right? In those 7 tuples, q sigma is nothing but an input alphabet, tau stack alphabet, del transition mapping function, q naught initial state, and z naught stack initial stack alphabet, and f. And here what the states are, what the set of states are. And for accepting the context free grammar, we're taking three states like in q0, q1, and q2. And the input alphabets are here, it was already there, 0 and 1 are the input alphabets. And stack alphabets are along with the 0 and 1, you need to define z0, because z0 initial stack alphabet, and del is always del. And what we need to do now, and q0 is in q0 where it is an initial state, and z0 is in z0 and stack initial state. And Q2, where Q2 is an final state. Here from Q0, Q1, and Q2, we're taking the Q2 is an final state. And how we define these three states, and how we define the Q2 is an final statements, that's that everything that we did from the context free grammar. And to accept such type of in context free grammars, and we designed the finite automatas, and from the finite automatas, we are getting the states of Q0, Q1, and Q2, and finally we choose that Q2 is in final state. That means the strings that are acceptable from the language and from the context free grammar, we define all these states along with the final state, right? So always the final state is a subset of the q, isn't it? So q2 is subset of the q. And initial states, the stack alphabets are 0 1 and z naught, and input alphabets are 0 and 1. So now what we are going to do is we are checking out the transition mapping function del. That means now we are defining the del. Let's see how to define the del. See, this is a way of defining or constructing the transition mapping function for the language WW power R, that is string reversal. Initially you need to may write like this. That means you need to write the stack symbol like this. Initially the stack contains z0, that is on the top of the stack. And this we can call it as an initial state of the PDA, where it is in q0. And now coming to the rules of this PDA, and where these rules are for the given language L, and the language L is for WW power R. And if you are having an Q0 and the input alphabet is an 0, if you the stack contains the top of the stack is Z0, then what the output of this is Q0 0 Z0. That means this input that we are pushing into the stack, now it becomes 0 Z0. And if you are reading with an 1 means, and now I am reading an 1 from my input alphabet, and it should push into the stack, and it becomes q0 1 z0. So these are comes under the first symbols push on stack. First symbols push on stack. First, if you are reading 0, then you need to push it. First, if you are reading 1, then you need to push it into the stack. And now coming to the grow the stack by pushing new symbols on the top of the world. That means W, the string part now. And Q naught 0 0. And already my stack contains 0, and my input I am reading it is in 0. Then this input is pushed onto the stack, it becomes 0 0. And here Q naught 0 1. Here I am having two alternatives. My top of the stack is 1 and my input symbol is 0. So it the 0 should be pushed onto the stack. Now it becomes Q naught 0 1. And now Q naught 1 0. That means now my input alphabet is an 1 and the stack alphabet is an 0. The top of the stack is 0. Then when I push it into the stack, then it becomes 1 0. And Q naught 1 1. Same thing. And both the input alphabet and the top of the stacks are same. And this is pushed onto the stack and it becomes 1 1. So these rules that we can call them as in grow the stack by pushing new symbols on top of the old string part. And if we are having an epsilons at the at the place of the input alphabet, then how you need to pop those? How you need to switch to pop mode? Q naught with epsilon comma 0. Then you need to change the state with an Q1 and what the stack alphabet is 0. That's the thing you need to write here. Q naught epsilon 1. You need to change the state with Q1 and what the top of the stack is here 1. So you need to write this. Q naught epsilon Z naught. You need to change the state to Q1 and what the top of the stack is Z naught. Then you need to write here. Right. So somewhere you need to do pops, right? These three rules can be called them, we can call them as a switch to popping mode. That is non-deterministically we are switching those. So boundaries between the W and W power R. So Q1 with you are having the changed state with Q1 and the input alphabet is in 0 and the top of the stack is 0. Now you need to pop these two and make it as an epsilon like Q1 comma epsilon. That means what we are doing here is we're shrinking the stack by popping matching symbols of W power R part. Up to this it is in string part, just it is in W. And from 7th rule onwards we are showing how to pop those, how to pop and how to make a change in the state. And then we can say that it is a string reversal. That means the part of the string reversal W power R. These three are between the W and the W power R, and this thing is totally comes under the W power R part, that is string reversal part. Right here we're having 10 rules that we define for the inputs along with the condition, along with the language. We define these rules. Totally we get 10 rules, right? We can use any of these rules to make the string acceptance. Is it clear? And this is nothing but an PDA rules for the string reversal language. And please make a note of this. Please make a note of these 10 rules, most important rules. I'm giving you time. Make a note of these 10 rules. And also we're having the two more rules for this. And what are those? See here. If it is 0 0, we make it as an epsilon. If it is 1 1 also, and for the changed state, we should make it as an epsilon. And if the further changed state like in q1 and the input alphabet is an epsilon and the stack, then the top of the stack is z dot, means you need to change the state to q2 like this, and then the top of the stack becomes z naught. So what we can say it as an, it can we call it as an enter acceptance state. That means we can accept the state in such a way. And please make a note of these two also along with the 10 rules. And most important rules, pda rules for the languages. You can use these rules for any type of languages, because these rules are acceptable for any type of languages. Just now we did it for the string reversal, but if you are having the input alphabets like in 0 and 1, and these rules are acceptable for any type of languages. And also if you are having the input alphabets like in a and b also, in the place of 0 you can use a, in the place of 1 you can use b, and the same outputs that you can generate like this, and you can define the rules like this, and you can show the acceptance of the pda, right? And if you note down these 12 rules, means it is very easy for you for designing the pdas and for showing the acceptance of the pdas. So that's why I'm asking you to note down these rules. These rules will be useful for you for further and further designing of the pdas for the given languages. And next it is an PDA as a state diagram on see all of you. And here we're having an PDA, and this is a state diagram. And always our transition mapping function is like this: del of some old state with the input alphabet along with the top of the stack is giving an output like a new state with the top of the stack, right? New state along with the top of the stack. And this you need to follow, this thing you need to follow. This is the transition mapping function. This thing you need to follow whenever you are designing the PDS, right? So here qi is an current state, and what the a is a next input symbol, and what x becomes the current stack, top of the stack. Or or y is nothing but that is the output state, that is an output, that's why we put it as an or y is nothing but a stack top replacement where the string y. And here from qy to we're showing an transition to qj is a next state, right? I think you all understand now clearly how to define this, the how to define the transition mapping function by using a state diagram. Qi with A along with the X. That means Qi with A along with X goes to Qj with Y. Is it clear? Qj with Y. So like that only you need to write. Like that only you need to write the uh, inputs along with the stack alphabet as well as with a new top of the stack. I think it is clear to you all. If you want to note down, please make a note of this also. This is an representation, a state diagram representation from the transition mapping function. And in this way, you need to write down like this. You need to represent like this. Qi is in current state along with the input symbol with the top of the stack and top of the stack, and it is generating an output where it is a new top of the stack y. That means the stack top replacement string y, and it goes to the qj. Qj is always a next state, right? And here this is a transition diagram for the string reversal. And in the last slide I show you how to uh, write the rules by using a transition mapping function, right? And in the last slide I show you how to draw the state diagram also. So with those two I am implementing here. I'm implementing a transition diagram along with the transition paths with the inputs along with the stack alphabets, right? See here, actually we defined three states, right? Q0, Q1, Q2, and also we define Q2 is an final state. So that's the thing we represented here. Q0 is an initial state, and from Q0 to Q1 there is a transition, and from Q1 to Q2 there is a transition, and Q2 is in final state. And up to this just we just draw a sequence like this: Q0 to Q1, Q1 to Q2, Q2 is in final state, where Q0 is an initial state. So initially we're starting with an epsilon, isn't it? We're starting with an epsilon, and our input is an epsilon, and our stack top of the stack is also z0, and whatever the thing that we need to return, the new top of the stack is also z0. So that's why we put epsilon comma z0 comma z0. That means q0 with epsilon comma z0 is z0, q0 z0. Is it clear? So initially we start with an epsilon. And now here we're having some different types of permutations and combinations. That means if it is 0, or if it is 1, or if it is 0 z naught, or if it is 1 z naught, or if it is 0 0, or if it is 0 1, or if it is 1 0, or if it is 1 1. And that's why we're giving it as a self loop for the q naught, because we are getting a return value, return state in the form of the output state, the output state which is the next state in the form of q naught. See here, whatever the things that we're having for the q naught, q naught, q naught, q naught, q naught, q naught, so these are the things that we're writing there itself. That's we did, nothing is there. And here we're generating the output in the form of state q naught. Here the output state is in q naught, here the output state q naught. And from 1 to 6, all these are all the q naught states. So that's why we put as an self loop, self. For example, 0 z naught we are getting 0 z naught, 1 z naught we are getting 1 z naught, 0 0 we are getting 0 0, 0 1 we are getting 0 1, 1 0 we are getting 1 0, 1 1 we are getting 1 1. But to which the output states are q naught, so that's why we put as an self state like this. That's why we put a self state like this. And also if we are having q naught epsilon z naught, then for that also we're having the rule q naught epsilon z naught. Q naught epsilon z naught is q1 z naught, right? So initially we're starting with an epsilon, that's why we put it as an like this: epsilon comma z naught, q naught epsilon z naught, it is z naught. Somewhere you need to do acceptance, right? Somewhere you need to make it as an acceptable state. So that's why we put like this. And then from q0 to q1, when I'm reading an q0 to an input epsilon, q0 to input epsilon with z0, with 0, and with 1, I am getting the output states. What output states I'm getting here? q0 epsilon, q1, q1, q1. That's why we make a transition from q0 to q1 with these inputs, right? The outputs are z0, q1 z0, q1 0, q1 1, right? So when we're reading the q1, when we're reading in q1 with zeros and ones, q1 with zeros and ones, then there we're getting epsilons, right? So for that we represent the transition self, because we're getting the output states as an q naught, that's why we put as an self. When the input and the output states are same, then you need to put it as in self states, self representations. So what it means is, for 0, for q1 with 0 and 0 it is epsilon, q1 with 1 1 1 it is epsilon, right? So now q1 with epsilon and z naught, it goes to q2, because we are making it as an acceptable states, right? So q1 epsilon z naught, it is q2 z naught. So that's why we make a transition from q1 to q2, where it is q1 epsilon z naught, it is z naught, right? And this is the way of representing a state diagram, that is a transition diagram for the language string reversals. What the thing that we did here is, first we define the rules. First we define the transition rules, and based on the transition rules we just represent the transition diagram like this. So here we defining what the input alphabets are, what the stack alphabets are, and finally what the queue, that is a finite set of states, q0, q1 and q2, right? Please make a note of this example also, it will be useful for you. And this is a transition diagram for the language string reversal. Previously I make you to understand how to write the transition mapping function rules. These are the rules, transition rules. And from these rules just I make you how to design the state diagram just by showing you with this example. And finally I implement that with the example of the given language string reversal. Is it clear? Please make a note of this. I think you all understand the concept of how to draw the transition diagram for the language, right? This is an PDA transition diagram. And now, see, which are growth stacks and which are switch to popping modes and which are pop stacks for matching symbols, and how to do the acceptance. This would be a non-deterministic PDA. And whatever the things we are learning now, yeah, under the concept of PDA, or whatever the constructions that we are doing for the PDA, all those are all the non-deterministic PDAs. So again we no need to learn the which is a non-deterministic PDA. Whatever the designings we are doing, all these are non-deterministic PDAs, right? So, and at q0 it is in growth stack. From initially we are growing, right? And here when we change the state means we did some poppings. So it is in final state. So here we go to acceptance. In between of these, we need to do some switchings for popping modes. So we need to do the transitions from Q0 to Q1 as well as from Q1 to Q2, right? I think you all understand the concept of designing the PDF for the given language as well as how to draw the transition diagrams for the uh, design rules. Design rules means those are the rules for the uh, given language, PDA rules. And let's see the example number 3, the language of balanced parentheses. I think you all know how to write the balanced parentheses. If you open one parenthesis means if you close the one, then it isn't balanced. If you open one, then if you close it two means that it comes under the unbalanced parenthesis. So now my inputs are in example number 3, my inputs that I am taking is in balanced parenthesis. And the input alphabets are these: open, closed, right? And coming to the stack alphabet, I am choosing both open and close as well as the Z naught. And here also I am choosing Q naught, Q1 and Q2 other states, because to make it as an acceptable, if I want to open, I need to do the transition between two states. If I want to close, I need to do the transition between two states. But in between, we're having in one state, and initially we start with one, and then you need to end with the another state. Then finally we are having only three states in the state diagram, in the transition diagram, right? So that's the thing you need to follow here. And open and close it, just make an assumption that it is a 0 or 1 or A or B. And whatever the rules, what are the 12 rules we're having, we designed for the language like in string reversal, those 12 rules are to be applicable for every language. As already said that those 12 rules are applicable for any type of a language. So I'm applying those rules here also, and I'm showing you how to draw the transition diagram for this example. See, grow stack again, switching to popping mode and pop stack of matching symbols, and same thing we did here. This is an, so we are making the loop transition from Q1 to Q0 also. So this is the uh, transition diagram, a PDA transition diagram for the given language of balanced parentheses, right? Is it clear? Initially, for the Q naught state, we're starting with an epsilon, and epsilon with Z naught is Z naught, Q naught Z naught. And open and closed we're having here, right? If open Z naught means it is open Z naught. If open means it is open. Only two we are taking here, not more than the other more combinations. We're showing the other more combinations to other states, right? And from Q0 to Q1, if you open, if you closed open, then it becomes epsilon, because both gets popped. Or epsilon Z naught means simply it isn't Z naught. And for Q1 it is open close means those two gets popped, right? Here we're doing the popping, and finally we're getting Q1 epsilon. And you need to change the state with Q2 when Q1 epsilon Z naught, then it goes to Q2 Z naught, right? So here we're having a transition from Q1 to Q naught. What the transition means, if you open from Q1 open, then it gives an state like an Q naught open, right? And if it is open Z naught, then it is open Z naught. See the transition here, Q1 to Q naught we did the transition. That means here also we are making the switching popping modes. That means after Q naught, whatever the things that we did, all those comes under the popping stacks for matching symbols. That means we are checking for how to pop it, and how to make it as an acceptance. So to go to acceptance by the final states, and when you see the stack bottom symbol, then it gets acceptable. So all these are all, we can call them as an allowing the adjacent blocks of the nested parentheses. That means we're allowing here just by drawing the representing the transition diagram or the state diagram like this for the language of balanced parentheses. And please make a note of this example also, it will be useful for you. And if you know the 12 rules, if you know the 12 rules of this PDA, then it is very easy for you for representing the transition diagram as well as for using the rules like open close, or open, or if it is epsilon z naught, and what the output that we are getting, all these will be from the already designed designed rules that we are using here. But what we are doing here is just we are showing the transition paths from state to state. And if you do the if you give the input for the state like this, means what the output you are getting. That's the thing where I'm showing you here. And for the just by representing the transition diagram or state diagram for the language of balanced parentheses. And actually you need to write the logics here, you need to write the logic, and you need to write the rules, and then you need to show the transition diagram like this. And already I show you the 12 rules, and those 12 rules are useful for every a type of a language. In the place of 0 0 1, you need to put open if the 0 is open and 1 is closed. Just make an assumption like that, and you can use the rules of those, right? Nothing will be happen, and those rules will be acceptable for any type of a language. I think you all understand this example also. Please make a note of this example. And in the next class, I will show you some other examples for the designing of the PDS. And then after making you to understand of these concepts, and also I will explain you how to do the acceptance by showing with an final state and by making the stack empty. And these two things I will explain in the next class. And then after I will go the most important concept of conversions between the CFG to PDA. And before that, what the thing that you all should know is that you all should understand is how to design the PDS from the given languages, and what the rules that we are following here. The transition mapping rules, is the mapping rules are suitable for all the types of languages or not. That's the thing you need to understand here, right? And then please all of you make a note of this example.